we are going to discuss one result based on orthogonal set. We discussed in the previous class what's the meaning of orthogonal set, what's the meaning of orthogonal vectors. Now, based on that, I written on the board one result statement. This result is very important in further problems. Easy to solve the problem to verify, especially for basis. Now, here what I written on the board in the statement is, if S is equal to V1, V2, etc. Vn is having a set n vectors, is an orthogonal set of non-zero vectors in an inner product space V, or V is a set of real numbers with dimension n. Then S is linearly independent. Suppose now here they taken, so S having n vectors is what type of vectors? Non-zero orthogonal set of vectors in an vector space, inner product space with the set inner product space of V defined on R with dimension n. Then first I have to show that S is linearly independent, and after that, and hence suppose is a linearly independent, then I have to prove that S is a basis for V. Keep in mind that S having some set of vectors, that vectors are non-zero orthogonal set of vectors is defined in inner product space. Each vector having how many components? N components, because we have taken R power of n. Suppose this set of vectors is a linearly independent, then I have to show that S is a basis for V. Suppose you prove this result, based on result we are easy to do that. If we want to verify whether the given set of vectors are orthogonal basis. Similarly, further we get orthonormal basis also. This basis is also called orthogonal basis, because it's based on which type of vector, set of vectors? Orthogonal set of vectors. Proof. Yeah, they given S having some set of n vectors. These vectors are orthogonal set of non-zero vectors and in a product space, or a set of real numbers with dimension. And first I have to show that or prove that S is linearly independent. If we want to prove that S is a linearly independent, now first we linearly independent means what? These now I have to it is enough to show that C1 V1 plus C2 V2 plus C3 V3. You already known that linearly independent definition in a first module in a product space, vector space. You already studied. Cn Vn must be equal to 0 for every Ci must be equal to 0. Then we say that the set of vectors V1, V2, etc. Vn are linearly independent. I want to prove this. Therefore, what we are going to do here, what's given here? Given S is equal to V1, V2, etc. Vn is an orthogonal set. I have written simply OS. OS means orthogonal set of non-zero vectors. You know, I already told in the previous class non-zero vectors. What's the meaning of non-zero? At least one of the component of V1, V2, etc. Vn is not equal to 0. But each one having how many components? N components, because R power of n. Now, from the definition of orthogonal set, inner product of Vi comma Vj must be equal to 0 for every I is not every I and j, for I is not equal to j for every I and j. Means inner product of V1 comma V2, V3 comma V2 like that, but not inner product of V1 comma V1, V2 comma V2. Now, for that's the meaning of orthogonal set means for a inner product of Vi comma Vj equal to 0 for I is not equal to j for every I and j. I and j may be any one of the value of 1 to n, because we are having n vectors. Okay. Now I am going to consider let. I have considered this part. Once you consider this part, now I have to prove that for every Ci is equal to 0, then we clearly consider S is a linearly independent. Therefore, I will choose let C1 V1 plus C2 V2 plus C3 V3 plus etc. Cn Vn must be equal to 0. I choose this part. What is my next step? I want to show that for every Ci must be equal to 0. Okay. Therefore, consider inner product of C1 V1 plus C2 V2 plus C3 V3 plus etc. Cn Vn comma Vi. I consider the inner product of sum of these terms comma Vi. But we already choose whatever sum of these values are 0, therefore 0 comma Vi. Yeah, they given already V is a inner product space. From the fourth condition or fourth property of inner product space, definiteness, inner product of u comma u equal to 0 if and only if u must be equal to 0 or any one of the component must be either first one position or second position 0, then you know that that must be 0. That is called definiteness. You know that this must be equal to 0. From the definition of inner product space, this must be 0. Definition of inner product space. Okay. The next is I go for additivity in the first slot. You already know that what is the second condition of this one, inner product of u plus v comma w, like that. Instead of v plus w, they are having n number of terms, that is all. From the additivity of the first slot and also additivity of the homogeneity of the first slot, from both the things, or first you take additive of the first slot, what do we get? C1 V1 comma Vi, this is Vi, plus C2 V2 comma Vi, C3 V3 comma Vi. Yeah, V1, V2, V3 etc. Vi is somewhere in between V3 to Vn. Therefore, I take etc. Ci, because C3 V3 Ci Vi comma Vi plus etc. Okay, plus Cn Vn comma Vi must be equal to 0. This is for additivity of the first slot, because since V is an inner product space. Next, homogeneity of the first slot, this can be written as C1 into V1 comma Vi plus C2 into inner product of V2 comma Vi plus C3 into inner product of V3 comma Vi etc. From the homogeneity of the first slot, Ci into inner product of Vi comma Vi etc. Cn into inner product of Vn comma Vi must be equal to 0. Okay? Because they given already V1, V2 etc. Vn are what type of vectors? Orthogonal set of non-zero vectors. Therefore, inner product of Vi comma Vj equal to 0 for I is not equal to j. Therefore, V1 comma Vi, 1 is not equal to I. Therefore, this is 0, this is 0, okay, this is 0 except Vi, Vi. I is equal to I only. Yes, then except Vi, Vi, everyone is 0. Therefore, what we get? This implies Ci into inner product of Vi comma Vi equal to 0. But we know that I is not equal to j equal to 0, I equal to j is not equal to 0. Therefore, see, A into B is 0 means at least A is 0 or B is 0, right? Both are not equal to 0, we can't write A, both are not equal to 0 means you can't write A into B equal to 0. Therefore, from the basic concept, Ci into inner product of Vi equal to 0 means this is not equal to 0, that implies which one is 0? Ci is 0 for every I. Now, we taken beginning, we consider C1, V1, C2, V2 etc. Cn, Vn equal to 0. Finally, we derived Ci is 0 for every I. Therefore, from the definition of linearly independent, the set having V1, V2 etc. Vn vectors are linearly independent vectors, because we choose C1 V1 plus etc. Cn Vn equal to 0 for Ci is 0 for every I, Therefore, from the definition of linearly independent, S is linearly independent. Next, hence S is a basis. Now, we prove that S is linearly independent. Now, before move to the next step, this is a very, very important. Again, I am going to recall for the steps within 1 or 2 minutes. Now, they given S having n vectors or orthogonal set of non-zero vectors in an inner product space, each vector having a dimension is n and a set of real numbers. First, I want to show that S is a linearly independent. What I did, now here I written already on the board what's the meaning of linearly independent. C1 V1 plus C2 V2 etc. Cn Vn equal to 0. It is enough to show that wherever is A is 0, then we say that S is linearly, when consider as S is a linearly independent. Therefore, they given S is a orthogonal set of non-zero vectors. From the definition of orthogonal set of non-zero vectors, what's the meaning of that? For inner product of Vi, Vj is 0 for I is not equal to j, for every I and j. Now, first I consider this part. My aim is I want to show that for every Ci must be 0. Therefore, what I did, now I consider the entire this comma Vi. This value already choose this 0. From the definition of inner product space, these values must be 0. At least one of the component 0, that inner product value must be 0. Next, from the additivity of the first slot, I written this step. Next, from the homogeneity of the first slot, I written this step. But you already written, yes, a set of vector V1, V2 are orthogonal set. From that concept, except inner product of Vi, Vi, the rest of the terms are 0 from the definition of orthogonal set. Now, product 0 means at least one is 0. This is not equal to 0 from the definition of orthogonal set. Which one is 0? Ci is 0 for every I. This gives the S is linearly independent. That implies S is linearly independent. Okay. S is linearly independent. Now, and hence S is a basis. You already know that in the module 1, when will we consider is a basis? Yes, S is a set of vectors you have. When S is a basis means it must be linearly independent and also spans V. S is spans V. S is spans V means choose any vector. You already know, we already shown that S is linearly independent. Now, suppose S is a linearly independent, it spans V, then we say that S is a basis for V. S is a basis for V. This is a concept you already known that in the first module. Even though you know that, I am repeating once again, S is a basis for V means it is enough to show that it is a linearly independent and also S is span V. We already verified that S is a linearly independent. It is enough to show that S is span V. What's the meaning of S is span V? I choose any vector in V, capital V, that vector can be written as linear combination of vectors of S. Then we say that S spans V. Now, I have to prove that S spans V. It is enough to show that I choose any vector, say let V belongs to V. That vector can be written as linear combination of vectors of what? S. Let V belongs to capital V, okay. Then it can be written as, I am going to choose this V can be written as linear combination of, I want to show that this V can be written as linear combination of vectors of V1, V2, V3 etc. V, and then we say that S is span for V. Now, I have to choose one vector, say V belongs to in capital V. That now I have to choose can be written as uniquely defined V is equal to C1 V1 plus C2 V2 etc. Cn Vn. I choose that. Okay. Next, I want to show that this V definitely is possible to express linear combination of V1, V2, V3 like that Vn. Then only we get is a span, S is span for V. Therefore, what I did, I taken one vector in V. Now, that can be written as this form I written, assume that. Now, consider inner product of V comma Vi. Consider inner product of V comma Vi. What is my V here? C1 V1 plus C2 V2, right? And then Cn, you substitute the V value, etc. Ci Vi, okay, etc. Cn Vn, comma Vi. Okay. As usual, what you did in the previous step, using additivity of the first slot, okay, and also take homogeneity of the first slot. Just few minutes before I discussed both additive of the first slot, homogeneity of first slot, are combining both the combination. This additivity of the first slot and homogeneity of the first slot, what we get, C1 into V1 comma Vi plus C2 into V2 comma Vi, etc. Ci into Vi comma Vi, yes, plus etc. Cn into Vn comma Vi, okay, inner product of that. Because V1, V2, V etc. Vn are orthogonal as a orthogonal set of non-zero vectors. From the definition of orthogonal set, everything is 0 except Ci. Therefore, inner product of V comma Vi must be equal to Ci into inner product of Vi comma Vi. From this, what is my Vi? Ci. Ci is nothing but inner product of V comma Vi divided by inner product of Vi comma Vi for every I. See, observe carefully here. V can be written as linear combination of V1, V2, V3 etc. means it is enough to find out the values of C1, C2, C3 etc. Cn in terms of V1, V2, V3. Then we say that is a linear combination of, you know that you already studied linear combination concept where in a vector space in the first module. See, once we get C1, C2, C3, C4 etc. Cn value in terms of V1, V2, V3, then we say that is can be written for what are the values of 3. Please try to understand. Suppose you have a vector V 1, 2, 3. Take two vectors, say V1 is 0, 1, 2. Simply I am writing, and then V2 is nothing but 4, 5, 6 like that. Yeah, V can be written as C1, V1, C2, V2. Now I have to find out for what are the values of C1, C2. Is it possible to express V in terms of V1 and V2? In terms of V1, V2. Then we say that V is a linear combination of V1 and V2. That C1, C2 is, we get a constant value. Why? Because V1, V2 are known. But here we do not know V1, V2, V3, each one having n components. Now finally we get Ci. Ci we get in terms of what? The values of V1, V2, etc. Vn. Definitely we get Ci values. For these Ci values, once you substitute Ci is this means we get C1 formula. What is C1 formula? Inner product of V comma V1 divided by inner product of V1 comma V1. Like that C2, C3. Each one we get a formula. For these values of C1, C2, C3 etc. Cn, we can be written as linear combination of vectors of V1, V2, V3 etc. Vn. Therefore, what actually S is? S spans V. S spans V, S is a linearly independent, that implies S is a basis for V. But S having orthogonal set of vectors, therefore, S is a what type of? Is an orthogonal basis. This basis is called orthogonal basis because the corresponding vectors having in S is orthogonal set vector, therefore, that basis is called orthogonal basis. Now, based on result, in any problem further, if you want to verify whether the given set of vectors are nothing but orthogonal, suppose some S or any W having some set of vectors, if you want to prove that is a orthogonal basis, it is enough to verify. It is enough to verify whether the given set of vectors are non-zero vectors and also orthogonal set. Suppose the given set of vectors are orthogonal set of non-zero vectors, immediately write the given set of vectors are orthogonal basis. From this result, is easy to prove that, not necessary to verify is a linearly independent and spans. From this result, We are confidently say that if you want to verify or if you want to prove any set of vectors are basis or orthogonal basis, it is enough to verify that given set of vectors are orthogonal set of non-zero vectors. Means each of the vectors are non-zero vectors and also orthogonal set of vectors. That give rise the corresponding set of vectors is an orthogonal basis for V. That is why I derived this result on the board is a very important. From this statement, I think everyone is clear. Finally, we get a basis. This basis I taken as orthogonal basis. Similarly, we have do it for orthonormal basis also, based on orthonormal set further classes. Okay. Now, I move to the next thing. Now, I am going to take one problem based on that. Yeah, that type of problem already I done in the previous class. Okay. Yeah, show that the following set is a basis for R power of 4 or V of R power of 4. Means each vector having 4 components. S having 2, 3, 2, minus 2. 1 0 0 1 minus 1 0 2 1 and also minus 1 2 minus 1 1. Yeah, I have to show that is a basis meant understood is a suppose this set is orthogonal, that basis is nothing but orthogonal basis. If we want to show that basis means first you have to verify whether these set of vectors of S are non-zero vectors. Yeah, non-zero vector. I told non-zero vector means how many components have? 4 components. Along with the 4 components, at least one component is not equal to 0. Then we say that the corresponding vector is a non-zero vector. All components are 0. For example, all components are 0. This is a 0 vector. At least one component not equal to 0, like that 0 0 0 1, like that. Yeah, observe, suppose I am going to take this is V1, this is V2, this is V3, this is V4, all vectors are non-zero vectors. We satisfy the first condition of that result just few minutes before we discuss. Okay. Next, I have to verify whether this set of vectors are orthogonal set, means it is enough to verify inner product of V1 comma V2. It's a row vector, just you take a dot product V1 dot V2. First component 2 into 2, 2, 3 into 0, 0. 2 into 0, 0, minus 2 into 1, minus 2, we get 0. Similarly, find out inner product of V2 comma V3. Yeah, just you multiply inner product V2 dot V3, multiply just corresponding components, 1 into minus 1, minus 1, 0 into 0, 0, 0 into 2 is 2, 0 into 2 is 2, 0, 1 into 1 is 1. What we get here? 0. Inner product of V3 comma V4. Okay. What is inner product of V3 comma V4? Take the minus 1 into minus 1 is 1, 0 into 2 is 0, 2 into minus 1 is minus 2, 1 into 1 is 1, we get 0. And next you take other possibility also, V1 inner product of V1 comma V4. What is inner product of V1 comma V4? First and last component, 2 into minus 1 is minus 2, okay. 3 2s are 6, 2 into minus 1 is minus 2, minus 2 into 1 is minus 2, we get 0. And then you take other combinations, yeah, V1, you are taken V1 with V2, V3 and V4, next move to V2, V2 you have V2, V3, you take V2 and V4, V2 and V4. Now, V2, V4, but you know that inner product of U comma V in inner product space must be equal to V comma U, both are must be same. You take V2 and V4, minus 1 into 1 is minus 1, 0 into 2 is 0, 0 into minus 1 is 0, 1 into 1 is 1, we get 0. Now, we taken all the combination V with that, V2, V3, V4, and then V3 and V1 is not there, we are going to take V1 inner product of, you have, inner product of V1 comma V3 has to find out. V1 with V2, V1 with V3 we don't have, okay. V3 we have, V2, V3 and V2, V4 you have, this is the last one, okay. V1, V3 I have to calculate. 2 into minus 1 is minus 2, 3 into 0 is 0, 2 into 2 is 4, minus 2 into 1 is minus 2, we get 0. We have taken all the combination V with V2, V3, V4 and V2 is V3, V4. Yes, totally we get 6 component and also V3 with V4. All the values are 0, therefore, yes, having V1, V2, V3, V4 is an orthogonal set of non-zero vectors. Zero vectors. This implies S is an orthogonal basis, or just you write basis, or just here is orthogonal, therefore I am writing orthogonal basis for R power of 4. Then easy to verify basis or not from that result. That's why we discussed that result. They are going to ask the result also, they proof, observe carefully. Okay. Now, based on this, what we derive the result? Suppose given set of vectors are non-zero orthogonal set that form a orthogonal basis. If we want to find out corresponding vectors, you know that C1 V1 plus C2 V2 etc. Cn Vn must be equal to V. Then how to find out Ci is nothing but inner product of Vi comma V, V comma Vi divided by inner product of Vi comma Vi. Using this formula, we have to find out the values of Ci. You know that how to find out Ci values in linear combination where in the first chapter. That is one method. Here another method you have, whenever the given set of vectors are orthogonal set of vectors, if you want to express any vector in terms of the linear combination, there how to find out Ci values? How to find out Ci values? This is an alternative formula for to find out Ci values. But in first chapter, we find out Ci values using system of linear equation, convert into echelon, convert into matrix form, augmented matrix form, and then apply elementary row operation, you convert it into echelon form, and then we have to find out Ci's values, C1, C2, C3, etc. That is one method. This is another method to find out the values of Ci. Suppose you have to express any vector in terms of the linear combination. How to find out the values for this? These values is find out using this formula only. This is alternative formula. Keep in mind, if we want to go for this formula to find out Ci values for express any vector in terms of the linear combination of set of vectors, that vectors is a basis, is orthogonal basis. Then we are using this as alternative formula. I think it's clear everyone. We are moving to the next concept. Okay. Yeah, before going to take next concept, now I am going to take one more problem. Just now what I explained, how to express any vector in terms of linear combination of other vectors using this formula. Okay. Yeah, the set S equals U1 comma U2 comma U3 where U1 is 3 1 1 1, U2 is minus 1 2 1, U3 is minus of minus 2 7 by 2 is an, yeah, just now we calculated is an orthogonal basis like that just few minutes before in the previous class. they given already, is an orthogonal basis. It's not given orthogonal basis, it is enough to verify these vectors are orthogonal or not. And also non-zero vectors is an orthogonal basis for R power 3 because each one they having 3 components. Express the vector y equals 6, 1, minus 8 as a linear combination of the vectors in S. In S. Yeah. They given already what are the vectors they have in S, U1, U2, U3. These vectors already given is a orthogonal basis. And also observe the orthogonal basis and also non-zero vectors. I want to express y in terms of the linear combination of this. Therefore, it is enough to take let y equals C1 V1 plus C2 sorry U1, C2 U2 and C3 U3. First you find out what are the values of CIs C1, C2, C3. Is it possible to express y in terms of U1, U2, U3? Now you have a general formula for whenever is orthogonal basis. If you want to express any vector in terms of set of orthogonal set of vectors, what's the formula? Ci is equal to finding Ci is inner product of V comma Vi divided by inner product of Vi comma Vi for every I. Okay. Now, this is a general formula, but here instead of V what you have Y. Therefore, what we are going to take here, this is a general formula what I written on the board, but we are going to write the formula based on this. What is V is Y, what is U1, Ui, right, divided by inner product of Ui comma Ui for every I. Okay. Now, first you want to find out C1. If you want to find out C1, what's the formula for C1? I need inner product of Y comma U1, U1 and also similar U2. Therefore, what are the value? C1, I am going to write the formula Y comma inner product of U1 divided by inner product of U1 comma U1, and then C2 is nothing but inner product of Y comma U2 divided by inner product of U2 comma U2. And then C3 is nothing but inner product of Y comma U3 divided by inner product of U3 comma U3. Okay, fine. Okay. Now, in the next step, first you find what are the values you need. First you find out inner product of Y comma U1. What is that is nothing but Y dot U1. Now, this is a column, therefore, you can't take dot Y transpose U1. What is Y here? Y is 6, 1 minus 8 into V U1. What is my U1? 3, 1, 1, 1. Yeah. Why I taken Y transpose U1? Because the given vectors are column vectors. What's inner product formula? Y transpose into U1. Multiply row into column. 3, 6 are 18 plus 1 minus 8. What's the value we get? That value is 11. Okay. 19 minus 8 is 11. Similarly, find out inner product of which value? U1 comma U1. U1 transpose into U1. What is U1 transpose? Row, column become row, right? 3, 1, 1 and also 3, 1, 1. 3 square, 9, 1 plus 1, we get 11. Okay. And also find out inner product of Y comma U2. Y transpose into U2. 6, 1 minus 8 into U2. What is U2? Minus 1, 2, 1. Multiply it. Row into column. 6 into minus 1. What we get? Minus 6. 1 into 2. minus 8. Yeah, minus 14 plus 2 is 12. Okay? Yes. And then inner product of u2 comma u2 I want to find out. It's nothing but u2 transpose into u2. u2 is a column become row minus 1 to 1 and then minus 1 to 1. Multiply it. 1 plus 4 plus 1. What we get? 6. And next find out the remaining. What's the remaining? Inner product of y comma u3 is nothing but y transpose u3. What is the y? Is 6 1 minus 8 into u3. What is u3? Minus of minus 2 7 by 2, right? Yeah, minus of minus 2 7 by 2. Multiply that. 6 by 2 we get minus 3. Okay. 1 into minus 2 is minus 2. And then observe here 8 you have, okay, 8 you have 8 into 7 by 2. 2 ones are 2 fours are 28. You have minus sign, minus 28. Observe carefully here. Now we get what actually this is a one of important thing, minus 7 by 2 into minus 8. Now 28, then add it, we get minus 33. Yeah. Similarly, I have to calculate what is inner product of u3 comma u3 is nothing but u3 transpose into u3 is minus of minus 2 7 by 2 into same thing minus of minus 2 7 by 2. Yeah. Otherwise, I'll do it this side. Yeah. This value, just multiply this row into minus plus 1 by 4, 1 by 2 into 1 by 2, 1 by 4, minus into minus plus 2, 2 into 2 is 4, okay, fine. And then plus 7 by 2 into 7 by 2, 49 by 4. Simplify that, finally we get minus, take LCM, now we have to simplify this, we get 33 by 2. Yeah, I will write it here. Inner product of u3 comma u3 is 33 by 2. Everything is written on the board here. u3 transpose u3, row into column, multiply it. What we get actually? 1 by 4 plus 49 by 4. Take LCM and simplify that. Finally, what we get? 33 by 2 we get. And next step, we have to substitute the values we get. What is C1? Inner product of y comma u1 divided by inner product of u1 comma u1. 11 by 11. We get 1. What is my C2? Inner product of y comma u2. This is a value 12 divided by this value divided by inner product of u2 comma u2 is 6. We get 2. C3. Inner product of y comma u3 is minus 33, okay, divided by inner product of u3 comma u3 is 33 divided by 2. We get minus 2. For these values of C1, C2, C3, y can be expressed in the linear combination of what actually vectors of u1, u2, u3. If you want to try the same linear combination, your first chapter, what is the first chapter? In a vector space, we get same C1, C2, C3, but you can't do it that method here because they given very clearly is an orthogonal basis. Keep in mind, is an orthogonal basis means what actually? You can't take to find out the CI values as usual method to convert argument matrix, convert it to echelon form. You must and should have to do it this form only. Therefore, before going to solve the problem, carefully observe that what they are asking, what they given, based on that carefully solve the problem. I think everyone is clear how we have to express in terms of the linear combination. Yeah. Now move to the next concept, orthogonal projection. Orthogonal projection we are going to discuss now. Yeah. This is one of the important concept orthogonal projection we are going to use in your course subject, where they are going to use linear algebra orthogonal projection. If you want to define orthogonal means is 90-degree projection, also projected at 90-degree only. Now here if you want to define orthogonal projection, now I have to choose two vectors. Let u and v be two vectors in an inner product space, over a space V of set of real numbers. Then, now I choose two vectors in an inner product space or a set of real numbers. Now, the orthogonal projection, of, there are two ways to define projection of u onto v. I am taking orthogonal projection u onto v is defined as proj of u with respect to v. Proj means projection. Projection of u with respect to v is nothing but inner product of u comma v divided by inner product of v comma v into v. This proj of u with respect to v is also denoted by u cap. There are two ways to denote notation for projection of u onto v. How to define inner product of u comma v divided by v comma v into v. This projection, orthogonal projection, is very important further also. Not only and also the component and the component component of u orthogonal to v. Orthogonal to v. Yes. For what component? What are the components is orthogonal to v is u minus u cap. What's the formula? U minus u cap or u minus proj of u with respect to v, means u minus inner product of u comma v divided by inner product of v comma v into v. This is a component to find out. This component is orthogonal to v, means what? Inner product of this component with v must be equal to 0. Means inner product of u minus proj of u with respect to v comma v must be equal to 0. Similarly, orthogonal projection of v onto v, onto u is proj of v with respect to u is nothing but v cap, is defined as inner product of v comma u divided by inner product of u comma u into u. Same way, and the component of v orthogonal to u, orthogonal to u is v minus v cap, is nothing but v minus proj of v with respect to u. What is the thing? V minus inner product of v comma u divided by inner product of u comma u into u. This component orthogonal to means it is the meaning is inner product of v minus proj of v with respect to u comma v must be equal to 0. See, sometimes they are going to ask to find out the component is orthogonal to v. It is enough to find out based on the projection of v with respect to u means find out v minus v cap. Projection of u with respect to means it is enough to find out u minus proj of u with respect to v or u minus u cap. Now, this is a way I to find out orthogonal projection. This is a very important this concept. In the next class, I am going to solve the problem, one problem based on that, how to find projection value based on that. Use Euclidean inner product space. Euclidean inner product space means the inner product space is defined on set of real numbers, that is called Euclidean space, inner product space. Then to find the orthogonal projection of u onto v, u onto v is u onto v means u cap is nothing but proj of u with respect to v. What is the formula? Inner product of u comma v divided by inner product of v comma v into v. Now, first you calculate what is inner product of u comma v. Now, they given row vector, just you have to write the dot product between that u dot v. What is u dot v? 6 into 1, 6. 2 2s are 4, 4 into 0 is 0, 10. Next, to find out inner product of v comma v means v dot v, that itself means 6 square 36, 2 square 4, 4 square 16, 10, 16 and then 56, okay, 40 plus 16, 56 only. Now, proj of u with respect to v is nothing but, what is the inner product of u comma v is 10 by 56 into v. What is v? V is 6 comma 2 comma 4. Then if you want to simplify further, you take it inside, what we get actually, then if you 5 ones, 5 5s and then 10, 2 5s and 2 2s and then 2 8s, 5 by 28. 5 by 28 of 6 2 4. This is a value of projection of u onto v. This is a projection of u onto v. Okay. This is a way. Similarly, try for projection of v onto u. You find out. I will leave it that part. Proj of v onto u is nothing but v comma u divided by inner product of u comma u into u. Do it similar way. V comma u, you know that. Only find out u inner product of u comma u. Then we get what is inner product of u comma u. Then very easy. A square 6 square plus 2 square. Yeah, projection of we did. No, 1 minute. Here we did mistake. V dot v. Yeah, v dot v. Inner product of v dot v is 1 square. Okay. 1 square. 1 square is 1, 2 square is 4 plus 0. Yes, this is 5. I did mistake here. Proj of u with respect to v is what? Actually, inner product of u comma v is 10 divided by 5. What is that? 2. Take 2 inside the bracket. 12, 4, 8 is the answer. Sorry, I did mistake here. Inner product of u v comma v is v dot v is 1 square plus 2 square plus 0 square. Proj of u with respect to v with respect to u means then you have inner product of v comma u is nothing but u comma v is 10. Only find out what actually inner product of u comma u. What is inner product of u comma u? Just now we calculated 36 plus 2, 4 plus 16. What we get? 56. 56 divided by, this is 10 divided by 56 into this. What I did? The same thing. Into, yeah, here I have to write v. Yeah, again I did mistake. Just a minute. Yeah. Here I have to substitute v, no? 1 comma 2 comma 0. What is that actually? 2 into 1 comma 2 comma 0. That is 2 4 0. Okay. Sorry. And then here I have to substitute 6 2 4. That's all. Yeah. Before going to wind up, I repeat within 1 minute. I want to find out proj of u onto v means uv divided by inner product of uv into v. I did mistake here. Inner product of v dot v comma v is 1 square plus 2 square plus 0 square is 5. Take that substitute and substitute v value, not for u value. Yeah, this is that. Similarly, proj of v with respect to u is nothing but inner product of v comma u divided by u inner product into u. This value, by symmetry, both the values are same, and then inner product of u comma u substitute and simplify that. Yeah, this is a way I to find out projection of u onto v or u onto v onto u or v onto u. Okay, thank you.